So let's look at number 19. Basically, number 19 says that we have a tank. Whoops. Sorry, that means I need to go home. But anyway, we have a tank of water that has brine in it, and pure water is coming into this at a rate of, let's see, 3 liters per minute. That's fresh water, so it's 3 liters per minute coming in. And water is also, the mixture of the brine, so there's 100 liters of brine. That should be a capital L, shouldn't it? 100 liters of brine in the tank. And that brine has 70 kilograms of dissolved salt, 70 kilograms of salt in there initially at time t equals 0. So basically, we've got fresh water coming in at 3 milliliters, or 3 liters, per minute, and it's kept uniform by stirring it up in there. So basically, the mixture is not going to have all the salt in the bottom, in other words, and it's going to run out at the same rate. So the question is, how many kilograms of salt are there in the tank at the end of 1 hour? So kilograms after 1 hour, well, if we're going to put this in minutes, so that's after 60 minutes to keep it consistent here. So that's the question, how many kilograms are in the tank at that point in time? So what we're going to do is we're going to let, we can say y, which is actually a function of t. So y of t would equal the number of kilograms of salt after t minutes. Okay, in the tank. We know that y of 0, which we could, if you want, we could write that y sub 0 is going to be 70. So we know there's 70 kilograms of salt originally in this tank. And then, of course, we're looking for y evaluated at 60. And so that's kind of the question mark, what we want to come up with to see what that is. So what we need to do is we need to utilize our formula here. And our formula, then, let me clear this off so we can get started. But basically, what we know is if we're looking at the rate of change of the kilograms with respect to time, we know that water is running out at 3 liters per minute. And so if we want to know the number of kilograms, how that's changing, basically what we need to do is we need to take the rate of change here would be 3 times. If we take y is the number of kilograms after t minutes and divide that by the 100 liters that are in the tank. So there's 100 liters in the tank. So the mixture there is going to be, this is the kilograms. There's y kilograms of salt and 100 liters after t minutes. And basically, I'm running out at the rate of 3 liters per minute. So anyway, this is 3 liters per minute running out. And that'll be negative there, right? So since it's running out, this is coming out of the bottom of the tank. So if we're looking at the tank, we have water coming out that has a mixture of salt in it. However, that mixture of salt changes as fresh water runs in from the top, right? So we're looking for how much does the kilograms per minute reduce. Basically, 3 liters per minute runs out, and it's going to be y kilograms of salt divided by 100 liters still in the tank at all times, since it's coming in at the same rate here. So this is equivalent to minus 3 over 100 is minus 0.03 times y is going to be the rate of change. So we've got dy dt, it's going to be negative since it's running out, 0.03 y. And then what we can do is we can use our theorem, and our theorem says, hey, if y is going to be greater than or equal to, or greater than 0, which it is because it's kilograms of salt in here, so we've got salt inside this brine mixture in here. So y is going to be greater than or equal to 0, and for any t greater than or equal to 0, of course, t is time, so that's going to be greater than or equal to 0. And furthermore, if we know that dy dt equals some constant times y, which that does up here, my constant is 0.03 here, then that's going to imply, this is going to imply that y equals y0 e to the kt. Okay, so basically what we can say here is y0 is the original if y equals y0 when t equals 0. So we know that y0 is 70. So what we can say then is we can come up with our equation that, hey, y equals 70. So the amount of kilograms, y, remember, is the amount of kilograms of salt in the tank after t minutes, is 70, which is the original one, y0. E to the kt power is right here because dy dt equals kt. So this would be to the minus 0.03 y. Excuse me, t power. Okay. So because it's to the kt here. So this is k. K is 3 here, so it's ky, k times y up here on this equation up here. Sorry. So it's anyway, y would equal, which is what we're trying to solve for, y0 e to the k times t power. So this is going to be the equation that we're trying to work with here. Y, which is the amount of kilograms of salt, equals 70 e to the minus 0.03 t. And then what we're going to want to do is we're going to want to plug in when t equals 60 minutes, right? So we're going to plug in t equals 60 minutes right here for t and come up with that. So I'm going to erase this so I don't have such crud on here. But we, once again, we had y equals 70 e to the minus 0.03 t power. And so when t equals 60, we plug that in right here for t. 60 times minus 0.03 is minus 1.8. So that implies y equals 70 e to the minus 1.8 power. And then, of course, solving for this, we just go ahead and calculate that. Should end up with our final answer of, and I assume this is what the book has, of approximately, so really this is y after 60 minutes, but anyway, this would be approximately 11.6, and of course, what's that? That's the number of kilograms of salt that's in the tank after 60 minutes. So what did we start with? We started with 70 kilograms of salt in there, but we were mixing in pure water at the same rate that that water was running out, and so we would expect that salt concentration to reduce there. So anyway, just trying to give you a quick little 10-minute blurb here, but anyway, that should be the amount of salt after 1 hour. So once again, what do we have to do? We had to come up with the rate of change of how much was coming out of the tank, and then utilize that and the theorem that we had at the beginning of this section to come up with the equation that then we could use. So